Hello everybody. In recent videos, we've talked a lot about matrix algebra, and one of the topics we talked about were linear functions, which had vectors as inputs and vectors as outputs. But for all of those functions, we'd usually multiply by a matrix. Starting in this video, we're going to talk about more general vector-valued functions. And in particular, we're going to shift our focus to more calculus-oriented topics, such as derivatives. So in this video, our focus will be on vector functions and derivatives. Now, in general, it's going to help us to be familiar with function notation. So this notation, f colon s arrow t, that means there's a function f which takes elements in the set S and returns elements in the set T. The set S is the set of input values, and sometimes called the domain of the function f. And the set T, the set of output values, that's sometimes called the range of the function f. Now, the most common types of sets we'll use in this class, we often work with a set R of real numbers, which is denoted with this fancy looking R right here with a double line on the left hand side. And in this class, since we're very interested in vectors, it'll help to look at this notation, R with the exponent n. That doesn't mean R to the nth power. What that means is the set of vectors with real numbers as its components. In particular, it will have n components. And in this course, we'll be focused on n equals 2 or n equals 3. So vectors with 2 real components or 3 real components. We might also sometimes use this notation. We might write the vector v is in the set Rn, which means that v is a vector which has n components. Sometimes we may write this using angle brackets and writing the elements horizontally. Or we might use square brackets and write the elements vertically. But in either case, we think of both these notations as representing a vector with n elements. Now, in previous classes, maybe in algebra or even calculus, you often would write functions with this notation. For example, f of x is equal to 2x plus 1. We're using our new function notation. We would write this as the function f has real numbers as input and real numbers as output. You can plug any real number into this function. Now, the vector functions, we've seen a few of them before. I'll often write the function with an arrow on top to indicate that the output is going to be a vector. And in this lesson and the next one as well, we'll look at functions which have a single real number as input, but the output is a vector. Now, we've actually seen functions like this before. Our main example would be lines in two-dimensional space, or more often three-dimensional space. And in the past, we wrote that as a script L. We didn't use an arrow notation before, but we might start using that notation now. Again, the function of a line has one real input, one real number input, and has a vector as output. Right? We would write L of t is equal to the slope vector m times t plus p, like a point on the line. So for example, we might have an equation that looks like this. L of t is equal to the vector 1, 2, 3 times t plus the vector 3, 3, 7. That's an example of a vector function. When we think of t as like time. At different times, you'll be at a different position in three-dimensional space. Here's another very useful example, the equation of a circle in two-dimensional space. In this case, I'll write this function as vector c, and one real number input, and a vector with two components as output. This function is vector c of t is equal to the vector cosine t sine t. And as we've talked about before, We specifically talked about this, I think the first time is when we talked about unit vectors, right? This represents the vector that makes an angle of t radians, for instance, with the x-axis. Right? If we were to graph all the points corresponding to the different t values, say in the range from t equals 0 to 2 pi, when t equals 0, the vector points here. Then as t increases, the points trace out the circumference of a circle with radius 1. When t equals pi over 2, that's a 90-degree angle, we're up here. As t increases to pi, we're at this point here, t keeps increasing to 3 pi over 2, we're at this angle, and then once t gets to 2 pi, we return to our starting point. And you could continue to increase the value of t, and you just traverse this circle again and again. Every multiple of 2 pi, you return to this point right here. One interesting thing about this equation is that all the points produced by this function, they also satisfy what you might know as the implicit equation for a circle. Now, you might have first encountered the equation of a circle as the set of points that satisfy the equation x squared plus y squared equals 1. Right? And if x is cosine t and y is sine t, and if we plug those values in here, right, cosine t squared plus sine t quantity squared, there's a trigonometric identity that tells us cosine squared plus sine squared is equal to 1. So in other words, these points also satisfied this equation. Just a different way to think about a unit circle. And as a more general example, any function you've seen before can be written using this vector function notation. So for example, if you have a function y equals g of x, you could write that as the vector function f of t. In this case, replace x with your parameter t, and then in that case, y is equal to g of t. And so any normal function could be represented in this form, but writing functions in this form has the advantage that you can express a lot more functions with this new notation we're learning. Here's one of my all-time favorite examples. And this is a function that you could never write as y equals f of x. Right? This is the equation of a trefoil knot, or a three-crossing knot. If you wear sneakers that lace up, this is often the first knot you would tie. Right? So it also looks like a pretzel as well. So you start off here, and as you increase the values of t in this function, you'll actually traverse this curve. And here t equals -2, then t equals -1, t equals 0, t equals 1, t equals 2, and it goes off towards infinity. Right, that's expressed by the function k of t equals t cubed minus 3t, t to the fourth minus 4t squared. And it's kind of hard to look at these equations and know that this is the type of graph that you're going to get. In order to produce graphs, you could generate a table of values and plot the corresponding points. So for example, you could let t equal -2 and calculate the x and y values and graph that point. Then t equals -1 and t equals 0 and 1 and 2 and 3. However, to get a really good idea, you'd probably need to graph values of points in between those. If you use a TI calculator, do they make those anymore? Do you use them, or am I being old-fashioned here? I don't even know. But if you have a TI graphing calculator, there's something called parametric graphing mode, which you can actually use to graph something like this. Or there's one of my favorite websites for graphing functions is desmos.com. And I think they also have an app for smartphones too that also allows you to graph parametric equations. It's slightly less tedious than this expression here. So as an example, if you want to see the Desmos application, this is the website desmos.com. Right? It asks you to sign in for an account, but you don't need to do that. You can just click on Graphing Calculator. you can actually enter parametric functions pretty easily. But instead of angle brackets, you would enter parentheses here and separate the functions by a comma. You will also have to specify the range of t values. Right? So for the trefoil knot curve, I specify the range of t values from -3 to +3. Right? And that traces out a graph of a trefoil curve, which is pretty neat. Now, heading back to slides. Right, so for vector function notation, there's a few ways we might write these. Right? We might write the vector function f of t as x of t, y of t. And you should think of these as functions. Right here, x of t is a function which produces the x values based on the parameter t. And y of t, again, is a function that produces the y values. We do often use the letters f and g and h for functions, but in this case, we're using the letters x and y to denote functions because they give x and y coordinates. Also, we might use something similar to vector notation, right? We might use the letter used for the vector function, but subscripts for each component. So the vector function f of t would be represented with the functions f1 of t, comma, f2 of t. And each one of these is just an ordinary function from R to R. It has one input, one output. Now, any vector operation that you learned can also apply to a vector function. So you might recall, let's say we have a vector v and a vector w. We have the operation of vector addition and the operation of scalar multiplication. You can do that with vector functions as well. So if we have a vector function f of t and a vector function g of t, we can add these two functions, right? F of t plus g of t. Sometimes you might see that written the quantity f plus g of t. And really, you just have to add the component functions. f1 of t plus g1 of t, comma, f2 of t plus g2 of t. Similarly, you can multiply a vector function by a constant. Right? C times the vector function f of t. Right? You could write that as c times f of t. You just multiply each component function by c as well. Right? So just for a simple example, let's say you have the function 2t plus 1 comma t squared plus 3 plus the vector function 3t plus 2 comma t plus 4. Well, for the first component, you would add 2t plus 1 plus 3t plus 2. That gives you 5t plus 3. For the second component, add together the two second component functions. So t squared plus 3 plus t plus 4. Added together, that gives you t squared plus t plus 7. And it's like adding vectors of numbers, except they're functions. Now, ultimately, we're going to want to do calculus on vector functions. And really, it's just like calculus on normal functions. You just have to do things more than once. You just do it for each component. So for example, limits are important. If you want to calculate the limit of a vector function, you just calculate the limit of each component. If you want to calculate the derivative of a vector function, and there's lots of different notations we might use. We might use vector f prime of t, or d vector f dt, or d over dt of vector f. And the definition is still the same. Right? Vector f prime of t is still the limit as h goes to 0. Vector f of t plus h minus vector f of t all divided by h. Right? You can do a vector subtraction and you can divide by a constant. It's like multiplying by 1 over h. And ultimately, if you carry the limit through to each of these components and then carry the dividing by h through to each one of these, you'll notice that the only thing which makes sense, the thing which happens, is the derivative of each of the components' functions. And this represents lots of different things. You can think of it as the rate of change of each coordinate of the vector function. And we'll also eventually talk about how this produces vectors tangent to a curve at a given point. Right? So if f was this winding light blue curve here, calculating the derivative at these different points would give you a vector which is tangent to the curve. But we'll have a lot to say about that in the next lesson. We're going to focus mostly on algebraic calculations here. Mostly we're going to need derivatives of polynomials, derivatives of sines and cosines. We might even do the derivative of e to the t at some point. We won't do anything really much more complicated than that. So here's some examples. Let's say we have the function k of t is equal to t cubed minus 3t, t to the fourth minus 4t squared. Well, the derivative, k prime of t, see the derivative of 3 squared is, the derivative of t squared is 3t. One more time. The derivative of t cubed is equal to 3t squared. The derivative of minus 3t, that's minus 3. The derivative of t to the fourth is 4 times t cubed. The derivative of minus 4t squared, that's minus 8t. Hopefully these derivative rules will come back to you if we do enough examples. What about the circle function? C of t is equal to cosine t comma sine t. Well, c prime of t would be the vector negative sine t and cosine t. Right? The derivative of sine is cosine. The derivative of cosine is negative sine. What about the derivative of the equation of a line? Right? One thing you could do, you could actually combine this expression by doing the scalar multiplication and the vector addition. So the equation of this line could be written as t plus 3, 2t plus 3, 3t plus 7, and then if you calculate the derivative of each part, you're just left with the coefficients of t, which is 1, 2, 3. Right? And you can almost see that in the original equation, right? This equation is really a vector of constants times t plus a vector of constants. And just like the derivative, if you were doing calculus 1, if you have the line y equals mx plus b, the derivative is m, the slope. Here, the derivative of the line is the slope vector. And so those are just some simple derivatives to get you started with this idea. Also, all the differentiation rules you learned back in Calculus 1, they all apply here. And so let's say we have two vector functions, f of t and g of t. And by the way, this works for vector functions in 3 dimensions as well. If you want to do the derivative of a sum, it's equal to the sum of the derivatives, even when they're vector functions. The derivative of a constant times a vector function is equal to the constant times the derivative of that function. Okay? Here's an interesting one. Let's say we have an ordinary function p, and so one input, one output value. So we can multiply a vector function by just a regular function. What happens if we take the derivative of this product? What is that equal to? It looks like the product rule, but is it? Well, the way we would figure that out, we would just do the math. Right? If we're calculating the derivative of a regular function times a vector function, well, we could go ahead and multiply that function p through to the vector function. Right? So each component is multiplied by t. And then we're calculating the derivative of a vector function. That's going to be the derivative of each part. And here I'm going to drop the of t. That just makes this a very long and hard to read expression. So we have the derivative of a product of regular functions, comma, the derivative of a product of regular functions. So in each component, the product rule applies. And so you'll have the derivative of the first times the second plus the first times the derivative of the second in that first component, and something similar for that second component, except f1 is replaced by f2. Now, these expressions, well, we can actually separate them. Right? Since there's a sum in each component, we can write this expression as the sum of two vectors. In particular, this first vector has a p prime, multiplied by each component, so we could factor out that p prime. But when we factor out p prime of t, we're left with the original vector function f of t. In the second vector, there's a factor of p. So we could factor out the function p of t. Then what we're left with, f1 prime and f2 prime, well, that's the derivative of the original function. And once we have it in this form, we can verify that, yes, the ordinary product rule also applies even if you're doing an ordinary function times a vector function. It's nice when math works out like that. So there's also something called the chain rule. You might remember, if you have a function within another function, how do you calculate its derivative? And so here, again, let's let p be an ordinary function, right? One input, one output. And f is our vector function, f of t. So the input for the vector function of f, that's just an ordinary number. So we could actually use the result of the function p of t and use that as our input for the vector function f. What's the derivative of this? It looks like the chain rule, but is it? Spoiler, yes. But in order to check that, right, we just do some algebra. In this case, if we have vector f of p of t, well, that means, first let's write out the definition of vector f, right? We can write that as the vector function f1 in the first component, f2 in the second component. But instead of f1 of t, we have f1 of p of t. Same thing for the next component. That's f2 of p of t. Calculating the derivative of a vector function, we just calculate the derivative of each part. But each one of these is an ordinary chain rule. Right? So the derivative of f1 of p of t is f1 prime of p of t times p prime of t. Right? The derivative of the outside function times the derivative of the inside function. And same idea for the second component. Once again, we have a common factor here, a p prime of t, so we can factor that out. But then we're left with derivatives of the original function applied to p of t. And so after factoring out p prime of t, what we're left with is f prime of p of t. And hey, that looks just like the chain rule. So again, multivariable mathematics is very consistent with what you've learned before. Right? The chain rule looks the same. Right? One more thing is, what if we have a dot product of two vector functions? Right? This is something very new in this course. What if we try to calculate the derivative of a dot product? Right? Is there a special new rule we need to memorize for that? Well, what we could do is check it with some algebra. Calculate the dot product of vector f and vector t. Right? It's the first times the first plus the second times the second. Right? Following that dot product pattern. And then we're calculating the derivative of this entire expression. Well, first we can use the sum rule for derivatives and split this into two parts. And then the derivative of each part, well, that requires a product rule. And we have a derivative of a product of ordinary functions. And so here we have f1 prime times g1 plus f1 times g1 prime, that first derivative. The next one is f2 prime times g2 plus f2 times g2 prime. That's the derivative of the next part. And what's interesting about this expression is we're actually going to rearrange part of it. It'll help us simplify. Right? f1 prime times g1, got a double underline, and f2 prime times g2. Right? If you look at this and this term, that's actually can be represented as this dot product with a double underline. Similarly, these squiggly underlines, f1 times g1 prime plus f2 times g2 prime, you can actually write that as this dot product with a squiggly underline. So it's a sum of two dot products. This is f prime dot g plus f dot g prime. And hey, that looks just like the good old product rule you learned in Calculus 1. And so the dot product rule for vector functions has the same form as the ordinary product rule. And so there's not really a lot of new things to learn, just a large number of old things to recall. And just for fun, because you learn math by doing math, right, let's try verifying that dot product rule with some actual functions. Right? In other words, going back to that previous slide, let's take two functions. Let's calculate f dot g prime, and let's also try calculating this expression on the bottom. And so we have a left-hand expression and a right-hand expression. Let's calculate it in two ways and show that we get the same thing. So it's always nice to be able to check your answers. So here, let's let the function f be 2t plus 3, comma, t squared. Let's let the function g of t be 5t to the fourth, comma, t squared plus 1. We calculate f dot g. We've got the first function times the first function plus the second function times the second function. When you simplify that, we get 10t to the fifth plus 16t to the fourth plus t squared. In order to calculate it in the other way, we'll need to calculate f prime. And so the derivative of this is 2, comma 2t. We'll need g prime. Derivative of g is 20t cubed, comma 2t. Right, so the derivative of the dot product, in other words, the left-hand side, right, is the derivative of this expression. Using our power rule, that turns out to be 50 times t to the fourth plus 64t cubed plus 2t. To calculate the right-hand side, we need to calculate f prime dot g plus f dot g prime. Right, and so we have all the ingredients. Here's f prime, here's g, and here's g prime. So we can calculate those dot products, right, like so, and then add together the results. I won't bore you by reading them all, but you can pause the video if you want and check the algebra. You'll find that the result you get is exactly the same as here, as expected. Mathematics is consistent. So just as an exercise, you should try something like this too. It'll be both good practice for dot products and also be good for calculating derivatives. So in this case, try using the functions f equals t squared, comma t to the fifth, and g equals t cubed, comma t to the fourth. So calculate this left-hand side, calculate this right-hand side, and make sure they're equal. All right, and that's an introduction to vector functions and derivatives. And in the next video, we'll move on to talk about things like tangent vectors and what this means visually speaking. But that's a good breaking point for this video. Thanks for watching.